Hello physics students. So in the first two videos of this topic we talked about electrostatic force. Two charges either pushing each other away or pulling on each other with equal forces by Newton's third law. But remember, in the first two videos I said that in this topic we're actually going to be learning four important ideas that we're going to use for a good half of this course. So force, yes, we already talked about that with the two videos. The next idea in this video we're going to learn about electric field. Electric field. And then we'll still have to talk about electric potential energy and electric potential, in other words, voltage. So four ideas today. The second, electric field. So what is electric field? Well, it turns out that our understanding of the interaction between two charges is too primitive. If you think about, say, two electrons repelling each other, so you say, okay, this one is directly pushing this one away, that's why there's a force that comes from this one. Well, it turns out that it's possible to pull this electron away extremely rapidly. And if you do it fast enough, you would see that for a small amount of time, there would still be a repulsion here on this electron, even though this charge is gone. And so for that slight amount of time, that means something else was there to actually create the force. That something else is the electric field. So that brings us to today, the electric field. So I'm going to pause in a second for you to copy these notes down, but let me just point out some key features. This is a positive charge like a proton. What I have near it are arrows pointing away from the proton, directly away. All these are equal length arrows. Further out, the arrows are shorter now, but at this radius they're all equal in length. And then further out, the arrows are all shorter but equal at this particular radius, all pointing outward. For a negative charge, it's the same diagram, but the arrows are flipped, pointing inward. So, jot these down and I'll talk more about electric field in a minute. Okay, so that is the electric field. What is it? It's some kind of disturbance that charge creates in space. So you don't need two charges. If you have a proton right here, all around it, it's done something to the space around it. That something is the electric field. It's a disturbance in space. We conceptualize it as an arrow, a vector, pointing away from positives or towards negatives. By the way, protons and electrons have equal magnitude charges. So the electric field around a proton is identical to electric field around an electron, only the arrows switch directions. But this is a pictorial or a visual representation of the electric field around positives and negatives. But of course, we want to do better than that in physics. We want to quantify it with a number. So this is how you would calculate the electric field. E, capital E, is the symbol for electric field. This is the 9 × 10⁹ coulombs constant. The charge that's creating the electric field over r squared. So it's like Coulomb's law, but there's no extra q here. And then the electric field, what it does is it creates force on charges given by this formula, F equals QE. Okay, so let me explain a little bit more in that what's going on. So let's suppose I've got a proton over here. If I put an electron here, we would say it's attracted to this proton. If I put a proton here, we would say it's repelled. That's the old way of thinking. Incomplete, inaccurate. The more accurate way, the way nature really works, is this proton creates a disturbance in the space over here, an electric field like this, given by K, Q over R squared. So that's the magnitude of the electric field. Make this green also to sort of better color coordinate it. So that's the electric field caused by charge 1. if I put an electron here, I won't put it right on because then it'll just look messy. I'll put it slightly below, but it's basically right on that arrow. The electrons feel forces in the opposite direction of the electric field, and that force is given by QE. So, rather than saying the electron attracts because its opposites attract, that's nice and simple. The true thing that happens is this. This is how you would actually describe how the force works. Charge 1 creates an electric field pointing away from it, and the electron feels the force in the opposite direction, the electric field to the left. Saying the same thing with more sentences, but it's the more accurate description. Okay? If instead I put a proton over here, again, I don't want to draw it right on the arrow because this is going to mess up the dry erase markers, but it's right on that arrow. What happens is protons respond to the electric field by moving with it. We used to say likes repel, right? But now we say charge 1 creates an electric field pointing away, given by that, and then charge 2, since it's positive, feels a force in the same direction as E, given by QE. And so you see, if I plug this whole expression here, I get KQQ over R squared, the same thing as before. So that's how the interactions really work. Creates an electric field, one charge, and the other one responds to the electric field. Okay. I've already paused the video for you to copy that down, so let's move on to our next example. Alright, so I've got a couple charges, a 3 microcoulomb and a 1 microcoulomb, both positive. On an x-axis, this is at the origin, that's at 0.2 meters. So, part A. Okay, so if you haven't already jotted this down, I'm going to pause here to give you an opportunity to catch up with the notes. Okay. So, what we do is we say, okay, at the midpoint here, I'm going to make a little space for the marker lines, but right here at the middle, this positive creates an electric field pointing away from it. And it has a certain magnitude which we have to calculate. So this I'll call E3 because it comes from the 3 microcoulomb charge. On the other hand, the 1 microcoulomb being positive also creates an electric field pointing away from it. So that's going to point this way. And I will call that E1. because again, it comes from the 1 microcoulomb charge. I need to find the lengths of those two arrows, and then you can see that I'm going to subtract them because they're in opposite directions. So the first arrow is from E3, let's do first. K, Q over R squared. So Coulomb's constant, 9 times 10 to the 9th, Newton meters squared over coulombs squared. The charge is 3 microcoulombs, so 3 times 10 to the minus 6th coulombs. And we're 0.1 meters apart, squared. 0.1 meters from the point, from the charge. Okay, so that gives us okay, let me just double check, make sure. Yeah, okay. All right, so that's the electric field, the green arrow over there. We need to find the electric field from charge 1. So we use the equation we learned today for the magnitude electric field, and we plug in Coulomb's constant, 9 times 10 to the 9th. One times 10 to the minus 6th coulombs, that's 1 microcoulomb. And this charge is also 0.1 meters away from the point in question. Yes, it's at x equals 0.2, but from here to here is 0.1. So again, we put in 0.1 here. And that's 9 times 10 to the 5th. Or if you want, I'm just going to keep it as 0.9 times 10 to the 6th to keep it the same power as that, because I'm going to now subtract them. Okay, so I have the two electric fields. As I said, I will subtract to get the net electric field. So I've got 2.7 times 10 to the 6th newtons per coulomb minus 0.9 and so I can express the net electric field like this in IJK form, as that's 1.8 in the positive x direction. So I write positive 1.8, 10 to the 6 newtons per coulomb I hat, and that means to the right. So I've just solved part A. If you didn't have a chance to jot this down yet, then I'll pause the video to give you a chance to catch up. Okay, part B. What is the force on a 2 microcoulomb charge? Once you have the electric field, you don't have to go back to Coulomb's law anymore. We could do KQQ over R squared, KQQ over R squared, and then subtract those forces. But why? We have the net electric field. We could find the net force by using this formula. So the charge placed in the middle was a 2 microcoulomb charge. That's that many coulombs. And the electric field there is 1.8 times 10 to the 6th newtons per coulomb. And you see the coulombs units go away. The 10 to the 6th, negative 6 go away. And what we get is 3.6 newtons in the x direction. So maybe we'll write it this way, 3.6 newtons I hat. Put a vector sign over there. I guess I could have put a vector sign over there also. Okay, so there it is. If you didn't get a chance to jot this down, then I'll pause the video here to give you a chance to catch up. Okay, let's do another example. Alright, so we're determining the location where the net electric field is 0, and it's the same, almost the same, well, the same charge situation that we had before. We have a plus 3 microcoulombs here, and a, you know what, maybe I'll make it a negative 1 microcoulomb here. Or you know what, I decided I'm going to switch to all symbols. So let's call this negative Q and plus 3Q, with Q obviously being 1 microcoulomb. And let's say that this is x equals 0, and this is x equals d. Now, we need to figure out what region contains a point where the electric field is possibly 0. It turns out that over here does not work. Well, first of all, in the middle doesn't work because the positive makes an electric field away from it like this, and the negative makes an electric field towards it that way. And there's no way for those two to be 0 because they're in the same direction. Over here, the positive creates an electric field pointing away from it. And the negative towards it. So you might say, hey, this is looking like a good region. Maybe they can equal 0 here. They cannot, because not only is this a smaller charge making the arrow shorter, it's also further away making the arrow even shorter. So there's no way for the electric field from this is always smaller than the electric field from that one. The only region is somewhere over here where this electric field points away from the positive charge, and the electric field from the negative points towards the negative charge. So it would go like this, and only here is it possible for those arrows to be the same size, because the smaller charge is offset by a smaller distance than this distance. So that's the region, somewhere from there. So we will begin by saying that E3 in that area is equal to E1. Okay? So, continuing on, K, Q, oh no, 3Q. Now, I'm going to call this distance x, because that's really what it is. It's how far we are from the origin. So that distance is x squared. Okay? On this side, we have K, Q, over. Now, what's the distance? Well, from here to here is the distance. And the whole thing is x. But we're subtracting off d. So it's x minus d. That's that distance right there. The radius that we plug in over here is x minus d. Now, I was meaning to say this in the last example also. I do not plug in negatives into this formula also, because remember that the electric field, you figure out the direction from your thinking about electric field pointing away from positives or towards negatives. And so once you figure out the directions of the arrows, you don't put a minus sign in, because then the direction has already been factored in, and putting a minus sign here is going to give you a nonsensical solution. We already included the minus sign by making this arrow point to the left toward the negative. So we don't add it again. Okay? So with electric fields, again, in kq over r squared, don't plug in minus signs. Just use that formula to calculate magnitudes. All right, so the k's go away, as does the variable q. And so we can cross multiply here and get 3 times x minus d squared. And on this side, there's only 1 here. Multiplied by x squared gives us just x squared. What I'm going to do next is take the square root of both sides. So I have radical 3, parentheses, the square root gets rid of that squared, x minus d equals x. I've got to distribute this through. Subtract the x, and add this to the other side. And then factor out the x here. And divide by that parenthesis term, giving us our final expression of So I write it this way, just lumping all the numbers together. So I have like 1 point something times d, so it's out here some distance beyond d. But you could put the radical d in the top here. It doesn't change the answer. It's the same thing mathematically. All right, let me pause here in case you need some time to catch up. Okay, one more example. So it's going to be similar to the example we did with force in 2 dimensions. We're now going to do an electric field in 2 dimensions calculation. Okay, and what are we talking about? So, So we want to know the net electric field right around there. Okay? That's at y equals a. This, by the way, is 2a and 2a. So this is at x equals positive 2a. This is at x equals negative 2a. And we've got a here. These are just indicating the distances. So, like in the example we did before, this creates, you know what, maybe I'll shift it up a little bit. Make a minus sign here. Just a little variety. In the last example, the forces were both like this. Now I'm going to make them a little bit different. So this creates an electric field pointing directly away from it. So here's the direction directly away from that charge, and it creates an electric field like this. Go too far. Okay. Let's call this E1. And this creates an electric field because it's negative pointing directly towards itself. So that would go like this. And I want to draw those the same length because they are the same length. And so what we need to do is add those as vectors. We can find the lengths from the formula kq over r squared, but in doing that, I'm going to just think of some components. I'm going to erase these, but I'm just going to sketch them in lightly for a second just to guide our reasoning. A little crooked. So this E has a rightward component and an upward component. This E here from the negative also has a rightward component, but it has a downward component. So this might be like 1,000 newtons per coulomb, and this be 1,000 newtons, opposite directions. They add to 0. The only components to survive are the 2x. So let's call this, well, I'll pick a more convenient. Let's say this is 3 and the other one's 3, so the total electric field would be 6 like this. So I'll sketch that in, the net electric field, like that, E net. And I'll put a theta over here as well. So what I need to do is find one of those x components and double it for the net electric field. Oops, I forgot that. If you haven't had an opportunity to jot this down yet, then go ahead and do that now. Okay, so the main idea I just expressed is that the net electric field will be equal 2 times the x component of one of those electric field arrows. And I can rewrite this as 2. The x component will be E cosine of theta in that diagram. Right? So E cos theta gives me that x component. I double to get the whole. Plugging in the length of that arrow is K Q over r squared. Now again, r is how far away that point is from this charge creating an electric field. It's along here, the hypotenuse. So the way I can find that is from the Pythagorean theorem. This squared plus that squared equals that squared. So I can say r squared is 2 the x squared plus the y squared. That's the hypotenuse squared. Okay? And once again, we can do that trick with the cosine. We can eliminate the cosine because this theta is the same as this theta over here. So if I redraw this triangle like this, A and 2A, this, if you square all this, it's 5A squared, and add it up. 4A squared plus 1A squared is 5A squared. Take the square root of that, and the hypotenuse is radical 5A. So the cosine of that triangle is the adjacent side over the hypotenuse. Adjacent side over the hypotenuse, which is radical 5A. So, once again, the A's here cancel, and On the top I've got 2 and 2, which is 4, multiplied together. 4kq. On the bottom I have 5a squared here, as I mentioned already, times the radical 5 is 5 radical 5 a squared. And that is the E net. We could even, if we wanted to get fancy, include the direction with the I hat there. Alright, if you haven't had an opportunity yet, I'll pause to allow you to jot this down. Okay, so that's it for today. We learned our second concept of our 4 big electrostatic ideas. We did force with 2 videos. We just did electric field, okay? And we still have potential energy and potential or voltage left to go out of the 4 main ideas. Again, I want to emphasize, just before we leave, that we don't say positive repel each other anymore. Okay, we say the positive here creates an electric field pointing away from it. The second positive feels a force in the direction of the electric field. Repel, right? If we put a negative here, it makes an electric field pointing towards the negative. We say negative, positive, attract. That's what we said before. Negative creates an electric field like that. When we put the positive charge here, then it experiences a force in the direction of the electric field attracted to the negative. A little bit more cumbersome, not as catchy as opposite attract, like repel, but that's the way the forces really work, the electric field. Okay, so that's it for today. I will see you in the next video.